The Galilean moons are four of Jupiter's largest moons. Despite their proximity to one another, they are fascinating due to their diversity. Among them are a moon with a volcano, the largest moon in the solar system, the moon with the best chance of containing life of any place we know of, and an even smaller, less well-known world in our solar system. Ancient, scarred moon whose surface can be traced back to the beginning of the solar system. This is Astrum, and I'm Alex Mullen. In this video, we'll take a look at each of these unique worlds, the innermost moon Io, and see why NASA and ESA are planning to send missions to study them this decade. Let's get to know Io a little better. Jupiter has 79 moons that. So far, we know of a handful of moons that orbit close to Jupiter within the planet's rings. Beyond that, there are four large moons called the Galilean moons, which are named after Galileo, who discovered them in 1610. The moons from innermost to outermost are Io, Europa, Ganymede, and Callisto. Beyond these, there are Jupiter's irregular moons, which are all much further away than the previous moons. Io orbits very close to Jupiter, only 350,000 kilometers above Jupiter's cloud tops. This means that Jupiter would appear 39 times larger in the sky from Io's surface. Jupiter is much closer to our moon than Earth, so it experiences 300% more tidal force than our moon does as a result of its proximity to the largest planet in the solar system. Our moon takes around 30 days to complete one orbit around the planet, while Jupiter takes only 425 hours compared to our moon's monthly orbit. At some points in its orbit, the tidal bulge on Jupiter can be as large as 100 meters. This effect is comparable to what we see on Earth, where the moon causes the ocean tides, although the effect is far less pronounced. Solar system Jupiter and the other large moons in the system prevent the moon's orbit from being any less eccentric, so Io won't be getting any rest anytime soon. The moon's size is comparable to Earth's moon, and it shares a similar orbital radius with Jupiter. Therefore, Io is neatly locked to Jupiter. Just as Earth can only see one side of the moon, so too can Jupiter. Density, which means it has a similar amount of gravity as Earth and the moon, but it has the highest density of any moon in our solar system. Its composition is mostly silicate rock and iron, like Earth and the moon, and it has the least amount of water compared to other moons in our solar system. Its core is probably made of iron or iron sulfides, and it is surrounded by There is a silicate-rich mantle and crust that surrounds the moon. The core is not believed to be convective because there is no magnetosphere observed in the lunar vicinity. The mantle is believed to be liquid near the crust and is at least 50 kilometers thick. This is the location from which all of the moon's volcanism originates. Now we reach the most intriguing aspect of Io, which is the hundreds of enormous volcanoes spread out across its surface. Little was known about Io until the 1970s, when telescopes began to pick up hints that the moon was waterless and that it may. Io has a sulfuric surface. The first mission to get a good look at it was Pioneer 11, but the quality was still lacking. What Pioneer 11 did find, though, was that Io is composed of silicate rock rather than water ice, and that it has a thin atmosphere. The next mission to Jupiter, Pioneer 10, was supposed to capture close-up shots of Io as well, but they were ruined by interference from Jupiter's radiation, which was 10,000 times stronger than the maximum radiation around Earth. In 1979, the Voyager 1 and 2 missions soared past Io at a mere 20,000 kilometers away, capturing breathtaking close-ups of the surface. What the spacecraft discovered was an awe-inspiring landscape abounding in vivid colors, devoid of impact craters. It also spotted mountains towering higher than Everest, vast volcanic pits, and what appear to be lava flows. Most significantly, plumes emanating from the surface confirmed that Io is indeed volcanically active, and the mission continues to this day. Voyager 1 saw this for the first time beyond Earth, excluding cryovolcanoes. It also confirmed that sulfur frosts cover the surface of Io, giving it its many spectacular colors. The sulfur compounds dominate the atmosphere. 2 spacecraft, one in July 1979 and the other at 1 million kilometers away, also observed Io in 1979. However, They only saw 7 of the 9 plumes that Voyager 1 saw in March. So, the volcanoes were likely active throughout that time. The Galileo spacecraft, which didn't set out to study Jupiter's interior, did produce some of the highest resolution images of the planet's surface during its 4-month stay there in 1995. Unfortunately, the spacecraft never reached its full potential due to a number of mechanical failures. Had it been fully operational, we would have had even better images. What the spacecraft did see, though, were plumes from numerous volcanoes and confirmation of the magma on Io is rich in magnesium and contains sulfur and silicate, just like on Earth. The surface of the planet is incredibly colorful, with yellow plains made of sulfur and white areas from fresh sulfur dioxide frosts. Radiation damages the sulfur, making the poles look redder than the rest of the planet. Red deposits from volcanic plumes that reached hundreds of kilometers in altitude are also visible. Elevated hundreds of kilometers above the Io surface, the most prominent deposit originates from the dormant volcano Pell. Unfortunately, Galileo was nearby, but Voyager 1 captured images of a 300-kilometer-tall and 1,200-kilometer-wide plume, roughly the size of Alaska, during its flyby. Interestingly, whereas on Earth, lava flows originate from depressions at the summits of volcanoes, on Io, there are instead large lakes of molten rock called lava lakes. With its towering walls and 200 kilometers in diameter, Loki is the largest volcano depression on the island. Its legs connect directly to the lava reservoir below, but there is typically a thin layer of solidified crust on top. Loki typically accounts for 25% of the average heat output of Io, but on rare occasions, the crust on a lava lake sinks back into the lake, causing Loki to produce 10 times more heat than usual. This phenomenon is most notably observed in one of Io's other big volcanoes, Tassa. Typically, this area features. While navigating to Pluto in 2007, the New Horizons spacecraft utilized Jupiter as a gravity assist. During its flyby of Io, it focused its lens on the volcano Tassa, which was mentioned earlier, and what it saw was truly remarkable. The plume could be seen hundreds of kilometers above Io's surface, and the crust is seen falling into the lava in this image, where there is only white. The radiant energy from the lava curtain was so intense that the camera only registered white. In addition to smaller eruptions around the moon, I've noticed some incredibly tall mountains on Io, the tallest of which stands at 18 kilometers. These mountains are often found alone, rather than part of a ridge or range. And although the majority of them aren't volcanoes, the presence of lava lakes nearby suggests that there are faults in the crust close to them. Another interesting thing about Io is how it interacts with The unusual aspect of this interaction is that when particles from Io's thin atmosphere and eruptions are lost to space, they float in orbit around Jupiter in a cloud that is known as a neutral cloud. This cloud can extend far beyond and behind the orbit of Io, and it also surrounds Jupiter in a donut shape made of ionized particles. Jupiter's magnetic field is enormous and strong. While Jupiter's plasma at Taurus rotates at a much slower rate, 17 kilometers per second versus 70 kilometers per second, it passes directly through the center of Jupiter's magnetic field. Particles from Taurus bombard neutral cloud particles, ionizing them and drawing them into Jupiter's plasma, where they are lost at a rate of approximately 1 ton per second. Jupiter's magnetosphere would be roughly the size of the Moon if it were visible to Earth's eye due to the rapid increase in the amount of matter passing through it every second. However, that's not all that Io does with Jupiter. Jupiter's magnetic field lines, which Io crosses, connect the neutral cloud in Jupiter's atmosphere to Jupiter's polar upper atmosphere, where they generate an electric current called the Io flux tube. A flux tube is essentially a concentration of the sun's magnetic field lines between sunspots, and the charged plasma that flows between Jupiter and Io creates an aurora trail around Jupiter's poles. This is the flux tube from Io hitting Jupiter's upper atmosphere. Additionally, you can see aurorae on Io, though they aren't limited to the poles. The colors green for sodium, red for oxygen, and blue for sulfur make it one of the most fascinating moons in our solar system. Europa is a stunning world teeming with life. We still don't know all there is to know about Europa, but there are many pieces of the puzzle that are beginning to fall into place. Let's start with where Europa fits into the Jovian system. Europa is the second and smallest of the 4 Galilean moons, although it's still the 6th biggest moon in the entire solar system. The Pioneer probe captured the first ever close-up image of Europa in 1973. Since then, the Voyager and Galileo probes have explored the moon, and with each visit, Europa has never failed to surprise us. Europa, a moon in the solar system located just behind Earth, has a diameter of approximately 3,000 kilometers and takes 35 days to orbit Jupiter. It's interesting to note that the first 3 Galilean moons, Io, Europa, and Ganem, are locked in a 421 orbital resonance as a result of their gravitational influences on each other. This resonance, along with the constant gravitational tugging from the other moons, prevents Europa's orbit from ever becoming entirely circular. This is because Europa has a slightly ecliptical orbital shape, which is impacted by a magnitude of gravitational force acting on it from. The moon's surface is stretched out by the tides caused by Jupiter's ebb and flow in its orbit, which are important because they affect both the moon's appearance and the processes occurring beneath it. Europa's surface is mostly water ice, and its long, continuous fissures and cracks, which are called liner, meaning lines in Latin, give it a striking appearance. We don't yet know how or why these linear features form on the moon, but one possible explanation is that, like ocean ridges on Earth, the gap is filled with warmer material as the crust separates from tidal flexing. In this image captured by the Galileo spacecraft, you can make out tiny dark brown spots called lenticula, which are believed to be formed by the upwelling of hot, molten rock. The material can rise to the surface by pushing the crust up or breaking through completely. If the material has broken through, we'll see bizarre terrains called chaos terrains. These are basically rough patches with a smooth surface around them. We expect these spots to be soft and hold important clues about what's beneath Europa's surface. Galileo data also suggests that the equator of Europa could be covered in. Europa, which is about the age of the solar system, has hardly any craters, just 50 major craters, in contrast to the Moon, which has over 5,000 craters with a diameter above 25 kilometers. This suggests that Europa's surface is continually changing and developing, as penitents, which are vertical cracks that can be as tall as 15 meters, are also found on Earth in arid regions at high altitudes. In terms of geological age, Europa is relatively young, with a surface estimated to be just 30 to 180 million years old, according to reforming models. What's more, its icy surface is the smoothest of any solid celestial object in our solar system, and its albedo, or light reflectivity, of 0.64 makes it 5 times brighter than our Moon. The surface is constantly and intensely bombarded by radiation from Jupiter, with the radiation level of the surface being one of the highest. A recent study from JPL suggests that Europa might even glow in the dark, energetic ions from the radiation that penetrates the surface, energizing the molecules beneath. The reddish-brown color spread across the Moon's cracks and fractures is believed to be due to salt and sulfur compounds mixed with water ice, which is then modified by Jupiter's radiation. The surface of Europa is equivalent to a dose of about 5,400 mZ per day of radiation exposure, which is enough to kill a human in a single day. Europa's atmosphere is composed mainly of oxygen, unlike Earth's, which is formed by radiolysis, or the process of radiation bombarding the water ice surface. This means that they release energy in the form of visible light. Unfortunately, Earth cannot see Europa's dark side, because we are always in the path of the sun. Future missions to Europa will be necessary to prove that the radiation received from Jupiter plays a significant role in Europa's atmosphere. After splitting the water molecule into its component oxygen and hydrogen, the former is able to evade Europa's gravity due to its low density, while the latter forms a diffuse neutral cloud that tracks Europa's orbit around Jupiter. In 2012, the Hubble Space Telescope captured an image of water vapor plumes rising up to 200 kilometers from Europa's south pole, In 2018, astronomers confirmed this. Further proof of Europa's water plume activity was found when researchers analyzed the old Galileo data using a new technique. By establishing a mission specifically to study these plumes, we can learn more about the moon's interior without actually landing on it. The most intriguing aspect of Europa, though, is the possibility of a global ocean beneath its solid ice surface. This would indicate the existence of a world beneath Europa's rocky mantle and water ice crust. Information about what lies beneath the moon's surface was gathered by the Voyager and Galileo probes in the late 1990s and 1979, respectively. In the time between these missions, there was a significant shift in the moon's magnetic field, which can only have occurred due to the presence of an electrically conductive fluid. Because Europa's crust rotates at an angle of 80 degrees, which cannot have occurred if the crust and rocky mantle were mechanically attached, scientists believe that the icy crust floats on the ocean and is. It is thought that Europa completes one full rotation around the moon every 12,000 years. The fact that its ocean is not attached helps to explain why there are so many linear features on the surface. Linear features should form at specific points on Europa due to tidal flexing, not everywhere. However, since the crust position changes over time, no one spot stays in the same place for long, so more and more linear features appear. Europa is 780 million kilometers from the Sun, which is 5 times further away than Earth, so sunlight reaches Europa. Europa, like all the moons in the Jovian system, receives very little heat from the Sun. As a result, the surface is frozen solid. The icy crust is as hard as granite, with an average surface temperature of minus 160 degrees Celsius at the equator and minus 220 degrees Celsius at the poles. However, the core of Europa is heated by the tidal pressures it experiences as it orbits Jupiter, so geothermal activity should keep the subsurface warm. Scientists believe that Europa's ocean is in contact with its silicate rocky mantle, making it an ideal environment for life as we know it. The ocean is believed to be submerged under only 15 to 25 kilometers of solid frozen crust and is approximately 60 to 150 kilometers deep. Interestingly, Europa is only a quarter of Earth's diameter, yet could contain twice as much water as all of Earth's oceans combined. Europa appears to possess all the necessary elements for life to emerge, including water, minerals, and energy. Based on the evidence we have seen thus far, scientists are highly confident in the existence of this ocean, the ability for chemical reactions to occur within it, and the possibility of geothermal activity on its ocean floor. Just as on Earth, entire ecosystems can thrive in such distant locations, far from the light of the sun. Therefore, Europa is currently considered one of the most probable extraterrestrial locations to discover life. Now, in 2022, NASA will launch the Europa Clipper spacecraft, which is expected to reach the moon by the end of the decade. It will conduct more than 42 flybys of Europa ESA. Additionally, in 2022, they will launch Jupiter's icy moons explorer, or Europa JUICE, which will explore Jupiter and its 3 largest moons, Ganem Callisto, Europa JUICE, and Europa. All 3 probes are specifically designed to study Europa's water plumes. And, in addition to the Europa Clipper mission, NASA is planning a Europa Lander mission, which will launch after the former. Both missions will shed light on Europa, our solar system, and its intriguing atmosphere, and we can only hope that they will confirm the most intriguing question: does Europa support life? At the very least, these missions will provide a fresh perspective on our solar system and its inner workings. Of the 79 moons that make up Jupiter, the third is Gamma, the largest of the 4 Galilean moons with a diameter of 5,268 kilometers, or, to put another way, 0.41 times the diameter of Earth. Gamma is also home to the largest ocean in our solar system. However, there's another intriguing mystery that lies beneath the surface of Gamma, setting it apart from everything else we've seen so far. The size of Ganem's atmosphere stretches hundreds of kilometers into space, giving the impression that it is larger than Titan, the moon previously thought to be the largest. Ganym's volume is even 26% larger than Mercury's, although it doesn't contain as much mass. Its average density is 19 g per centimeter cubed, compared to Mercury's 54 g per centimeter cubed. Ganym's composition is similar to Europa's, with a thick crust of water ice extending 150 kilometers deep beneath the surface. This is thought to. Mercury is mostly water and rich in dense metals, but the oceans of Ganem have so much water that their average density is much lower. The oceans of Ganem are so large that they contain more water than all the oceans and seas on Earth. They are also estimated to be 100 kilometers deep, which is 10 times deeper than the deepest point in our ocean. Because of all this water, Ganem is only 50% rock, and the rest is water with small amounts of metals and other substances. I find it fitting that the moon Ganem, whose name comes from a myth in which Zeus, or Jupiter, as he was known to the Romans, kidnaps a boy named Ganem and makes him a cupbearer for the gods. Jupiter, interestingly enough, has an atmosphere that contains oxygen, so it's not out of the question that life could exist on Ganem, what with all that water and the oxygen atmosphere. First of all, the oxygen atmosphere on Ganem is extremely thin, estimated to be between 0.2 and 12 micropascals, or about 100 billion to 500 billion times lower than Earth's atmosphere pressure at sea level, making life on the planet extremely unlikely. Secondly, although ecosystems on Earth have proven to thrive in deep oceans without sunlight, there may be a significant obstacle on Ganem that makes this impossible. Europa, Ganem's neighboring moon, is recognized as a more promising candidate for life due to its thick ice layer between its core and the ocean. However, if Ganem's ocean is salty, and there is mounting evidence that it is, then life at the ocean's depths could potentially survive. The interior makeup of Ganem could be significantly altered by the presence of a salty ocean. Models indicate that the island may be composed of multiple layers separated by ice sheets. If this is so, the innermost layer could potentially be in touch with the rocky core, which would greatly enhance the likelihood of life there. However, beneath the ice and water of Ganem, there is something incredibly surprising, something that scientists still don't know how to explain: a magnetic field. Science made a groundbreaking discovery in 1996 during the Galileo spacecraft's flybys of the icy moon. The presence of auroras is a strong indicator of a magnetic field. Surprisingly, scientists were able to detect auroras in Ganem's tenuous atmosphere. What's more, after extensive study by Hubble, it became apparent that the auroras weren't wobbling as much as expected. This is likely due to magnetic friction in the salty water ocean beneath the surface. As the feature on Earth that shields the planet from solar radiation allows all life to flourish, the field surrounding Game does not entirely shield it. Being encased in Jupiter's extremely powerful magnetic field and radiation belt means that it is still being bombarded with a lot of radiation. The surface of Game still has about 5 to 8 rem, which is enough to severely illin or kill a human in just 2 months. However, it is still better than its closer orbiting neighbor moons, and scientists aren't entirely sure why. We experience this magnetic field everywhere on Earth because electrons are moved by molten convection currents within the hot core of our planet. However, scientists believe that the core of Game, which is smaller than Earth, should have cooled down sufficiently to become a solid mass rather than a liquid by now. This would prevent electrons from moving through convection and the formation of a magnetic field. Interestingly, none of the other moons of. The reason behind Jupiter's magnetic field is still a mystery, but one possible explanation could be tidal heating, which occurs when Ganem, the only moon in our solar system with a magnetic field, experiences increased gravitational attraction at certain points in its orbit relative to Jupiter and its neighboring moons. Ganem orbits Jupiter approximately once every 7 days in an eccentric orbit, meaning that it is closer to Jupiter at some points than at others. In the same way that mass is drawn in the direction of gravity, an object's shape changes as it moves away from the source of gravity. Since Ganem is in an eccentric orbit around Jupiter, it experiences constant stretching and contracting. If you've ever played with a blue attack in your hands and then pushed it back into a ball shape, you might have noticed this phenomenon. Ganem has formed an orbital resonance with two of its fellow Galilean moons, Europa and Io, in what is called a loss resonance. This means that every time Ganem orbits Jupiter, Europa will orbit exactly twice and Io exactly, which causes tidal heating. After a while, it gets surprisingly warm because stretching causes friction as the material rubs up against itself. On the scale of planets and moons, this friction adds up to a tidal force, creating heat through friction, which is known as tidal heating. This mathematically precise configuration has occurred 4 times, which is not a coincidence. It is evidence of the moon's gravitational pulls on each other and the system's attempt to conserve the resulting momentum. This means that Ganem is constantly being pulled by its neighbor's gravity and is under a lot of gravitational stress. One possible explanation is that tidal heating is warming up Ganem to a point where its core remains a liquid, allowing it to continue producing its magnetic field. Maybe you've noticed that Ganem's surface is divided into 2 sections, one that's mostly dark and the other that's mostly light. By comparing the amount of impact craters on each, scientists have determined that the darker section is older because it has more craters. On the other hand, the lighter section may have fewer craters, but it does have long ridges and grooves that reach up to 700 meters in height. Impressive sight, stretching thousands of kilometers in length, but scientists still don't know how the ridges formed. One theory is that the moon's surface was stretched out during an unstable period in the moon's ancient history by tidal forces. Another theory is that the core of the moon was warmed and its magnetic field preserved by the same forces. Whatever the case may be, the magnetosphere of Ganem has been instrumental in helping scientists understand the moon's composition by measuring the areas where aurora borealis appeared in the moon's atmosphere. The existence of subsurface oceans on Ganem was confirmed by scientists without ever setting foot on the planet. As for the remaining mysteries of Ganem, maybe the Jupiter Icy Moon Explorer will shed light on them. The EA spacecraft is scheduled to launch in 2022, but it will take another decade before it reaches orbit around Ganem. Its purpose is to study the inner workings of several of Jupiter's moons, including Gando, but until then, we might have to settle for Callisto's description as a mystery. The third largest moon in our solar system, Callisto, is just slightly smaller than Mercury at 4,820 kilometers across. Despite having a diameter that is only 58 kilometers less than Mercury's, it has only 1/3 of Mercury's mass. Most people would be hard-pressed to provide any facts about the largest moon that we know of. Is it just a dull world, or do we simply not know much about it? Actually, we know more than you might first assume, and it is far from boring. Let's begin with its place in the Jovian system. At an average distance of 19 million kilometers, Callisto still remains neatly locked with Jupiter, meaning that the same side of the moon always faces its parent planet. However, this does not mean that Callisto is locked in an orbital resonance with the other 3 Galilean moons, and we do not believe that it ever was. Callisto is the second largest of these moons. It takes 17 Earth days to orbit Jupiter. The atmosphere is composed of carbon dioxide and possibly oxygen as well. However, oxygen has not yet been detected. What is known is that the atmosphere is extremely thin, so the molecules within do not collide. According to theory, the atmosphere should be stripped away by processes of atmospheric loss in just 4 years. Scientists believe that the surface of Callisto is replenishing the lost atmospheric particles through sulfation of carbon dioxide, as shown by some intriguing surface features. Now, Callisto is one of the oldest objects in our solar system, with evidence indicating that it is more than 4 billion years old. The speckled surface of Callisto is immediately noticeable, as it is covered with impact craters of varying sizes. In fact, it is nearly saturated, meaning that any new crater would likely just overlap an existing one. Since there has been no geological activity on Callisto, cratering is likely the only process that has had a significant impact on its appearance. Callisto's surface is relatively old in comparison to other bodies in the solar system because, on geologically active planets like Earth, processes can erase nearly all evidence of past impacts. This is due to the fact that Earth experiences a lot of surface erosion due to weather, water, plants, volcanism, tectonic plates, and human activity. Even other Jovian moons, like Europa or Io, have relatively fewer surface erosions. Callisto is unlike other planets in the solar system in a number of unique ways. Firstly, it has no visible signs of geological processes like volcanism or plate tectonics, which means that its surface has stayed intact throughout the years. Secondly, there are no mountains on Callisto's surface, suggesting that when the planet first formed, it was probably an ocean world. The surface of Callisto has been frozen over for a long time, and aside from the meteor showers, nothing has changed. Let's take a look at some of the craters, though, because some of the larger ones are impressive structures. For example, Asgard is 1,600 kilometers across and the second largest impact crater on the planet, and Valhalla is 3,800 kilometers across and the largest multi-ring impact crater in the solar system. Something else about these craters is that the impact factor was big enough to potentially puncture the thin crust, which was then refreezed in the light patches in the center. When you zoom in on these regions, you'll see that they have a mild appearance. The contrast between the bright knobs and the darker plane is noticeable, and these regions are much less created than the rest of Callisto's surface. This makes sense if the plane is a refrozen surface, therefore it's likely that it is too. The rings, which are located on Callisto but a billion years younger, are probably cracks in the crust, a concentric collapse in the moon's fragile shell. Interestingly, these bright knobs are still visible within the rings. What are they? We don't know why they have degraded so much over time, but it could be because of micrometeor impacts, the ice is slowly sublimating, or some other reason. The upper planes are more illuminated than the lower planes, possibly because the rocky debris from meteors and micrometeors has gradually rolled down the knobs, exposing the pure ice at their peak. Intriguingly, most impact craters on Callisto are shallower than on our moon. For example, the Lewin impact structure is more than 100 kilometers wide, but only 600 m deep. This could be because the impactor was fragmenting before it hit, leading to a more dispersed shot and consequent effect on the Earth's surface. The surface may have leveled off from subsequent larger impacts, or the impact may have occurred more than a billion years ago. Nonetheless, the ejector trailing off the impact is still visible, providing further proof of the remarkable stability of this moon. Other features, such as the enormous dome in the moon's center and the presence of concentric rings and a raised peak, are typical of large impacts on other worlds. Just like on our moon, Callisto has some large craters with pits in the center instead of peaks. One example is Tinder. Why does Callisto have such unusual craters? It could be because its crust is thin and brittle, with either soft ice or a salty ocean underneath. Estimates place the crust thickness at 80 to 150 kilometers. This information comes from the Galileo space probe, which spent years orbiting Jupiter, devotes a considerable amount of energy to studying the Galilean moons. Galileo discovered that Jupiter's magnetic field couldn't reach Callisto, which means that there's a conductive layer at least 10 kilometers thick under the surface. This couldn't have happened in ice or silica unless the ice layer was partially molten or extremely large temperature gradients could be maintained below the ice to create a conductive effect. Additionally, data suggests that Callisto has a small silica core at its center with a radius of approximately 600 kilometers. It raises the question of whether Callisto, like other frozen worlds with water mantles beneath their surfaces, could support life. We know that in order for life to exist, there must be liquid water and energy. Callisto is approximately 800 million kilometers from the Sun, so it receives very little heat from our star. Additionally, there are no tidal forces, so there is no way to warm this subsurface ocean, if it even exists, other than radioactive elements. Unfortunately, even visiting Callisto wouldn't solve this problem. The lack of evidence suggests that the environmental conditions required for life on Callisto are less favorable than on other icy worlds. This is in contrast to moons like Europa and Enceladus, which have vents that release water directly from their subsurface oceans, allowing scientists to study their habitability potential without ever setting foot in the oceans. But we shouldn't overlook Callisto either, as its 19 million kilometers orbital distance from Jupiter puts it outside of Jupiter's main radiation belt, making its environment thousands of times more hospitable to human exploration than that of Jupiter's inner moons. Callisto also contains a lot of water ice, which can be used to make propellant and, of course, is essential for human survival since it separates hydrogen and oxygen. Callisto's geological stability would make surface construction relatively worry-free, and the absence of massive mountains or deep trenches would make travel from Callisto faster, easier, and more efficient. From here, we could safely explore the inner Jovian system or use it as a jumping-off point for further exploration of the outer solar system, thanks to its low gravity and the possibility of a gravity assist from a close flyby. While Galileo accomplished a commendable job studying Callisto during his flybys, there are still many information gaps about Jupiter. Hopefully, we will receive that from the European Space Agency's Jupiter Icy Moon Explorer, which is set to launch in 2022 and reach the Jovian system by 2030. The mission will explore Jupiter and its 3 largest moons, including Europa, Callisto, and Ganymede. With that, we hope you've learned all there is to know about the Galilean moons of Jupiter in our solar system's vast expanse, orbiting ring giant Saturn. ESA plans to make multiple close flybys of Callisto during this mission, which could shed light on questions like whether or not the moon has an ocean beneath its surface and whether or not it can support life. Here on Saturn's second-largest moon, Rhea, you're more likely to hear of its larger sibling, Titan, but Rhea is intriguing in its own right and holds many mysteries and wonders, such as ice cliffs hundreds of meters high, an internal structure that defies scientific models, and a mysterious discovery that surrounds this moon, which is just as strange as the thing we didn't find. Now is the time to learn everything there is to know about this moon, Shadow, as it moves away from its larger sibling, Rhea. Rhea, named after the Greek goddess Titan, has long fascinated astronomers and space enthusiasts. It was discovered on December 23, 1672, by the Italian astronomer Giovanni Domenico Cassini, who made many important contributions to our knowledge of Saturn and its moons. My name is Alex Milan, and you are watching Astrum. Join me on a journey of discovery to the Saturnian system and the moon Rhea to see what scientists have found there and to experience its beauty firsthand. For generations, planetary scientists have studied Triton, Saturn's largest moon, with a diameter of 1,528 kilometers, roughly half the size of our moon, and an orbital distance of approximately 527,000 kilometers. It completes one orbit every 45 Earth days. It is locked in a synchronous rotation with Saturn, meaning that the same side always faces the planet. This is a common feature among large moons in our solar system. Solar system. Rhea's surface is exceptionally reflective, reflecting 70% of the sunlight that hits it. Its composition, mainly water ice, contributes to this high reflectivity. However, this does not mean that Rhea is devoid of features. On the contrary, the moon is adorned with numerous craters that bear witness to its violent past and ancient impacts. The largest of these craters, namely Malmaldi, spans an impressive 480 kilometers, approximately the same size as the distance between Harris and Amsterdam. These craters provide valuable insights into the moon's history beyond their scars on the surface. Composition observations have revealed that the bottoms of certain craters appear darker than the surrounding terrain, suggesting that impacts may have exposed darker amorphous water ice and impact melt. In this particular photo, you can observe a crater in the southern hemisphere of Rhea surrounded by bright. Rhea's system of bright wispy streaks that crisscross its surface is one of its most intriguing features. These streaks were first observed in detail by the Voyager space probes in the early 80s, but their true nature wasn't understood until the Cassini mission provided high-resolution images decades later. Initially, these wisps were thought to be deposits of frost or ice. However, they were later discovered to be ice cliffs, some hundreds of meters high. These cliffs are probably the product of tectonic activity on Rhea, where the icy crust fractured and a tenuous atmosphere, or exosphere, appeared to surround Rhea in 2010, according to data from the Cassini spacecraft. While a small amount of gas is expected around the Moon, the amount that was detected was surprising. The detected atmosphere, which mainly consisted of oxygen and carbon, provided insights into the Moon's geological history and the processes that have shaped its surface over billions of years. One theory proposes that the oxygen is created by the decomposition of water ice on our surface when it is struck by ions from Saturn's magnetosphere. On the other hand, carbon dioxide is believed to be the result of organic molecules on our surface being oxidized by the oxygen in the atmosphere. There are intriguing questions about the origin and sustainability of this atmosphere, given that oxygen is about 5 trillion times less dense than Earth's atmosphere at sea level and incredibly thin. While we can't see what's beneath Rhea's icy surface, scientists have used a variety of methods to infer its internal structure based on its average density of 123.6. This discovery made Rhea the first moon known to have an oxygen atmosphere outside of Jupiter's moons Ganem and Europa. It also opened up new avenues for research into the complex interactions between Saturn's moons and the planet's powerful magnetosphere. With a G per cubic cm that is just slightly higher than water, we can infer that water ice makes up about 75% of Rhea's composition. A smaller fraction of rocks makes up the remaining 25%. This structure has led to the Moon's description as a frozen, dirty snowball. In contrast to moons like our own Moon, which are mainly rocky bodies, Rhea ranks lower in the SDK. Spectroscopic observations confirm that water ice is the dominant component during Cassini's visit. Scientists have found a variety of materials on Rhea, including carbon dioxide, trapped in the surface ice. This finding challenges the idea that Rhea's ice is pure water and instead contains other compounds, such as complex organic molecules, which could explain its higher moment of inertia. The majority of scientists believe that Rhea is not differentiated into layers, but some have questioned this model. Rhea's potential habitability and the conditions needed for liquid water in the outer regions are both cast in doubt by a 2006 article in the journal Icarus that proposed the existence of a subsurface ocean beneath the Moon's surface. While this theory is still in its early stages and lacks the solid evidence of the subsurface oceans on moons like Europa and Enceladus, it remains an intriguing prospect that future missions may explore. Rhea's shape is rather peculiar compared to other large moons and planets in our solar system. It's slightly flatter at the poles and more elliptical near the equator, giving it a trawl ellipsoid shape. What's even more perplexing is that Rhea's back shape doesn't quite line up with what we'd expect given its rotation rate. This discrepancy has prompted scientists to speculate that Rhea may have an internal structure that isn't uniform. With denser material concentrated away from its center, Rhea has experienced some exciting flybys in recent history. One of these was on January 11, 2011, when Cassini, a joint project of NASA ESA and the Italian Space Agency, spent over a decade studying the Saturnian system, including multiple close encounters with Rhea. The most recent close flyby was on January 9, 2011. We got our best look at Rhea's surface features yet during Cassini's flybys in March 2013, when the spacecraft soared past RAR at a height of 997 kilometers above the Moon's surface. The close approach allowed the spacecraft to take extremely detailed images of the Moon's man-made terrain, as well as data about the Moon's composition, including the fact that it does not have an internal magnetic field. The images showed a landscape that was dominated by two types of terrain: older, more rugged areas and younger, smoother plains that have been seen in earlier Voyager missions. We previously discussed areas that are believed to be very old, possibly even from the beginning of the solar system. These ancient surfaces record the intense bombardment that happened when the solar system was young. On the other hand, smoother plains are likely the result of a resurfacing event, like material ejected from large impact events. This material would have fallen back to the surface, filling in old craters and creating smoother regions. However, one of the most interesting things that Cassini missed was any signs of rings around Rhea. This theory was put forth by scientists in 2005 in response to unusual electron density measurements around the planet that Cassini had taken. However, during its flyby, Cassini failed to detect any rings around the rear of the object. While this doesn't necessarily mean that there isn't a day disk there, it does make the likelihood of its existence much lower. Another interesting thing about the rear is its location in Saturn's intricate system of moons in the E-ring, a diffused ring of ice particles thought to be supplied by Enceladus cryovolcanic eruptions. Although Rhea does not appear to be geologically active like Enceladus, its interaction with the E-ring particles ensures that it does so constantly. Despite being at the outermost extremities of the ring, where the ice is densest, this interaction has the potential to influence the moon's backside characteristics and add to its brilliance. From its somewhat smooth side to its tenuous atmosphere, and its place in Saturn's complex system of moons, Rhea continues to intrigue scientists and spark our imagination. However, our exploration of Rhea is far from over. Many questions remain unanswered, such as what the exact nature of its interior structure is and how it has become so obscured in comparison to its more well-known siblings. Evolved over the billions of years since its formation, could it harbor simple forms of life in a hypothetical subsurface ocean? These and other questions will be explored by future missions to the Saturnian system. Although no missions are currently scheduled to specifically study Rhea, any spacecraft sent to study Saturn and its moons will most likely observe it. Music. As we come to the end of our journey to Rhea, let's pause to appreciate the diversity of worlds in our solar system, from the hot surface of Venus to Rhea, with its icy surface reflecting the distant sunlight, stands as a testament to the beauty and mystery of our universe. From the icy plains of Pluto to the towering volcanoes of Mars and the potential subsurface oceans of icy moons like Enceladus, our cosmic neighbor is filled with wonders waiting to be explored. Who knows what secrets this distant moon may yet reveal? Well, everyone, it's Titan, your most requested video, and I must admit, I can understand the curiosity. It is the only. Unlike Jupiter's 4 Galilean moons, Saturn's 6th spherical moon Titan has an atmosphere, stable bodies of surface liquid, and best of all, humans have visited the moon, so I'll be able to show you plenty of real photos and video footage. Stay tuned for all the information you could ever want about Saturn's largest moon, Titan. My name is Alex Mullen, and you're watching Astrum. When compared to Titan, the other moons of Saturn are dwarfs. To give you an idea of its size, its diameter is half that of Earth's moon, and its mass is 80% greater. Titan is the second largest moon in our solar system, behind Jupiter's moon Ganem. Titan's thick atmosphere makes it appear slightly larger than Ganem, but its actual diameter is much larger. Titan, which is 40% as massive as the Sun, is still bigger than Mercury, the smallest planet, but its gravity is only 0.14 gs, or 135 meters per second squared, even weaker than that of our moon. This suggests that Titan is composed of roughly half water ice and half rock. Like other celestial objects of its size, Titan is believed to have a differentiated interior, meaning it has layers. One of these layers is believed to contain. Titan's atmosphere was found to contain extremely low-frequency radio waves by the Cassini spacecraft orbiting Saturn. Titan's surface is not known to be a good reflector of these waves, but the liquid interior of the moon suggests that there may be a liquid ocean beneath the crust that contains water and ammonia. This ocean is similar to Earth's magma layer, which is located between the core and the crust and has been turned liquid by heat pressure and, to some extent, tidal forces. There's also the fact that the moon's surface features have moved up to 30 kilometers since Cassini began taking pictures, which could mean that the surface isn't actually attached to the core, but is instead floating on top of this liquid ocean layer. Despite the lack of evidence for life on Titan, scientists think the conditions could be ideal for subsurface ocean life. Unfortunately, we'll have to wait a while to find out if there's any. Exploration missions to Jupiter's Europa are more likely to investigate the possibility of life in the near future. Titan's differentiated interior does not generate a magnetic field, but the Moon is still shielded from the solar wind for 95% of its orbit around Saturn, within Saturn's own magnetosphere. Titan circles Saturn once every 15 days and 22 hours, and its orbital eccentricity is rather large, meaning that its orbit isn't circular and that its orbital plane is also at an angle. Titan is not likely a captured object, though. Just like Jupiter's Galilean moons, Saturn is believed to have once had multiple large moons. However, these moons were destroyed in large collisions, leaving Titan as the only survivor. Saturn's medium-sized moons, such as Ius and Rhea, are believed to be remnants of this turbulent past. Titan's day is the same length as our moon's orbital period, meaning that its rotation is tightly locked to Saturn's. Titan's hazy atmosphere obscures the surface from outside views, but it's possible to see Saturn from Titan itself, though the view would be severely limited. This does mean, though, that standing on Titan would make it appear as though Saturn's limbs were permanently attached to the surface, eliminating Titan's haze. Now we come to one of the topics that truly distinguishes Titan from. Titan, like all the moons in our solar system, has a substantial atmosphere. I'll never forget being astounded by the first photo I saw of the moon because I had always assumed that moons couldn't possibly have atmospheres. I had assumed that Titan must be some newly discovered planet. What strikes me as peculiar about Titan's atmosphere is how far it stretches into space. Compared to Earth, you can see that it forms a tight fit around Titan on the surface. On the other hand, Titan appears to be covered in a thick blanket. This is due to several factors. Firstly, Titan is significantly smaller than Earth, but its atmosphere is 19 times more massive than Earth's, or 73 times more massive per surface area. Secondly, Titan has much weaker gravity than Earth, so it doesn't drag it down as much. The mass of the atmosphere results in a surface pressure of 145 atmospheres, which is 45% higher than the atmospheric surface pressure on Earth. Titan is a super rotator, meaning its atmosphere rotates faster than the planet itself. This is particularly noticeable at the poles, and when compared to Earth, whose mesosphere extends 600 kilometers into space, Titan's mesosphere stops at 120 kilometers. Even at 975 kilometers, the Cassini spacecraft had to make adjustments to maintain a stable orbit against atmospheric drag, much like Venus. While the Moon rotates every 16 days, the polar vortexes at each pole spin once every 9 hours, giving the impression of perpetual hurricanes. So, what exactly is in the Moon's atmosphere, and why is it orange in color? Well, it's mostly nitrogen, with a small amount of hydrogen and some trace amounts of hydrocarbons from the breakdown of methane in the upper atmosphere caused by ultraviolet light. These hydrocarbons are responsible for the orange hue. Titan's orange hue is believed to be caused by the constant breakdown of methane into hydrocarbons. Since the Moon should have run out of methane within 50 million years, a relatively short period when compared to the age of the solar system, some source must be replenishing the methane. Cryovolcanoes are the most likely candidate, although biological life is still a possibility. Methane in the atmosphere creates a greenhouse effect, lowering Titan's temperature. Without this, the haze, but conversely, haze. Titan's surface receives only about 1% of the sunlight that Earth receives because of its reflection of sunlight. The Haiyan team compared the difficulty of taking photos at this light level to taking pictures of an asphalt parking lot at dusk. However, this is offset in part by the anti-G greenhouse effect, which cancels out some of the potential greenhouse effect from the methane. Titan is so frigid that any water on the surface stays solid and never melts, evaporates, or sublimates. So, why do we occasionally see clouds on Titan? Well, those are actually methane clouds, which means that it can rain methane on Titan. Titan's temperature is just right for methane to be liquid, and it freezes at Titan's surface temperature is minus 1825 degrees Celsius, and its boiling point is minus 1615 degrees Celsius. This, along with the moon's high surface pressure, has scientists excited about the possibility of hydrocarbon lakes or seas on Titan's surface, which would be the first time anything like this has been seen outside of Earth. This was a major motivation for the Cassini mission, which aimed to explore the moon's thick atmosphere in search of life. The astronomer who found Titan in 1655 created a probe that would enter Titan's atmosphere and land on the surface. The probe's designers factored in the possibility of landing on an ocean when they were making the design. After nearly 3 hours of descent, the probe finally touched down on Titan's solid surface. Although it couldn't see any lakes, the probe did confirm that methane lakes once existed. The probe landed on what looked like a dried-up lake bed, and the stones you can see in the surface photos are. From its vantage point in space, Cassini confirmed that Titan still has methane lakes. Close to the South Pole, the spacecraft spotted an area that turned out to be a lake named Ontario Lacus. At 15,000 square kilometers, it's 20% smaller than its North American namesake, but still fairly large. On one side of the lake, you can see the smooth shoreline that has been worn down by the waves. On the other side, you can discover the initial signs of a river and delta on Titan. This means that liquid hydrocarbons flow from higher planes to the lake, where they deposit in the delta, just like on Earth. On Titan, the lake is very shallow, with a depth of only 40 centimeters to 3 m at its deepest point, and just over 7 m at its shallowest. According to Cassini's radar mapping, the lake does not have waves larger than 3 millimeters, so its surface appears flat, like a mirror. This doesn't imply the size of the waves observed on Titan should be larger than those on Earth due to the planet's dense atmosphere and strong gravity. However, since the North Pole of the Moon was emerging from a 15-year winter, another lake called Jingpa Lacus was discovered. As Cassini passed by the Moon, sunlight reflected off the surface of Jingpa Lacus, creating a mirror effect. The Cassini spacecraft captured additional images of Titan's flowing liquid, which led scientists to conclude that the North Polar region of the planet is home to Liam Mar, the second largest lake on the Moon, with a surface area of 126,000 square kilometers. Although some areas of the lake are relatively shallow, the average depth is 50 meters, much deeper than Ontario Lacers, and some areas could reach depths of. There are several rivers that flow into the lake, which is over 200 meters in length. In this area, you can also see large islands. One interesting observation Cassini made, which he called the Magic Island, was the appearance and disappearance of what looked like an island. Scientists don't know for sure what happened, but they speculate that subsurface ice rose to the surface as the lake warmed during the moon spring, or that silt became suspended in the lake bubbles. It's still a mystery. Titan's largest lake at the Kraken Mare, a lake covering 400,000 square kilometers, is divided into two main parts by a narrow band that resembles Earth's Strait of Jalta. This band is nicknamed the Throat of the Kraken due to the lake size and the fact that it's believed the tide changes by about 1 meter. Because of this, the band may be subject to strong currents and even whirlpools. The Kraken Mare is also relatively deep compared to Ontario Lacys, although it doesn't go deeper than 170 meters. So we now know about the lakes on Titan, but Titan's surface is so young, as little as 100 million years old, that it must be geologically active. Some scientists think the dirty ice crust is exceedingly rigid, but there's evidence of tectonic activity on the Moon, maybe due to tidal forces with Saturn. The main factor that renews the surface, though, is probably the same thing that produces methane in the atmosphere, cryorays. Titan's cryovolcanoes release magma that is similar to Earth's, but instead of molten rock, it contains a mixture of water and ammonia. As it flows out of the vents, it cools to a surface temperature that allows it to replenish the surface. Unlike Earth's lava, Titan's magma is less viscous, so it flows farther than Earth's. As a result, Titan's mountains are flatter and will never reach the heights of Earth's volcanoes.